Hi, so in this section we'll look at how hierarchical clustering works. So some of you would have already covered this in other modules, but not all of you. And I also want to show its relationship to omics data. The hierarchical clustering is used extensively to detect subtypes of disease. So you may have a collection of cancer samples of the same type, like leukemia, and this unsupervised method allows you to detect whether the samples contain a number of subtypes of leukemia. So let's move on. So the motivation for hierarchical clustering is to group together samples which show similar gene expression profiles into a hierarchical tree. Also, we can group together genes that have similar behaviour across different samples. So there's these two different ways of using hierarchical clustering with a gene expression matrix. Similarity between gene expression profiles will be measured using a distance metric or measure. We're going to sort of graphically show this with a very small number of samples, 3 ALL and 3 AML patients, and also a very small number of genes. But in reality, you can do this with a large number of samples, and we'll see it with the GoLab data where there is 30 samples, and you can do it with thousands of genes. So we'll consider this scenario: 6 samples named ALL1, ALL2, ALL3, so these are lymphoid leukemias, and AML1, AML2, AML3, so these are myeloid leukemias. And we're going to only consider 10 genes, named gene 1 to gene 10. So we have two approaches. We can either cluster samples, and then we consider the 6 samples as 10-dimensional vectors, each consisting of 10 expression values for all the genes in the sample. Or we can cluster genes, and in that case we consider 10 6-dimensional vectors, each consisting of the expression values of over the 6 samples. I think this is easier to see when we show a gene expression matrix. So the columns are different samples and the rows are different genes. So this is actually, in a sense, the opposite to what you would expect in machine learning, where the rows are often samples and the columns are features, and in this case the features are genes, gene expressions. So in microarray omics data analysis, we quite often sort of invert these. The samples are columns, the genes are the rows. So if we want to cluster samples, we're considering these vectors, all of consisting for each sample all of the genes, the gene expression for all the genes. If we want to cluster genes, we're considering these vectors, which are essentially the gene expression value for that gene across all of the different samples, and the expression value for that gene across all of the different samples. How do we measure similarity between vectors? Well, I think from machine learning modules you'd be familiar with this, but so you've got the normal Euclidean distance between two n-dimensional vectors, also called the L2 metric, or we've got the Manhattan block distance, a city block distance, n-dimensional vectors A and B, L1 metric. So these are common metrics between measuring distances between vectors, but For microarrays, we often use something a bit more complex. So this is the Pearson's correlation, and we use what is often called Pearson's correlation sort of distance. So we do 1 minus the Pearson's correlation. So how does that work? Well, if we have say a gene which goes up and then down again, and we have another gene that does the same, goes up and down, if you look at the correlation between those, it's roughly 1. So if you have 1 minus 1, the distance is 0. So if they're doing exactly the same, distance is 0. If one is going up and then down, and the other one is going down and then up, the correlation between them will be minus 1. So we have 1 minus minus 1 is a distance of 2. So that's the maximum distance between them. If they're doing something which is not correlated, just going up and down, this is 0, so it's got a distance of 1. So it gives you a sense of a distance between gene expression profiles that have different shapes. How correlated are the shapes, which is typically what you want to do. Now another metric, so this is useful, for instance, to if you've got a gene regulating another 10 genes, you expect those 10 genes to be co-regulated. They're all regulated the same way, and they should all go up and down at the same time. So this would detect co-regulated genes as clustered together, showing the same shape across different samples. Now another metric is absolute value Pearson's correlation metric, where we do 1 minus the absolute value of the correlation. So can you think what biological situation we would use this metric for? It's not sort of obvious. So this metric is particularly useful if we want to cluster together co-regulated and anti genes which are potentially positively regulated by a single transcription factor, but that transcription factor may also inhibit other genes. So we might actually get a pattern where one goes up and the other one goes down, and we want to give that a close distance so that these cluster together as well. So if we use the absolute value, so that correlation would be minus 1, but then this would be 1, and it gives it a distance of 0. So genes that are close together, if they have a strong correlation, so they might be co-regulated, but they're also close together if they're anti-correlated, so they may be regulated by an inhibition in the biological network. So these are the key distances that we use for gene expression data. How do we measure the distance between different clusters? Well, there's lots of different approaches. I mean, we've got a distance metric which gives the distance between any 2 points in a high-dimensional vector space. But what we want to do is somehow work out the distance between a cluster and another cluster. So we have single linkage, where it gives the distance between these clusters as the distance between the 2 closest points in them. We've got complete linkage. The distance is the farthest points in both clusters. And then there are some other distance metrics. But microarray data, often we use complete linkage. So what's the difference? Well, this really gives you a sense of what is the distance between the 2 most dissimilar things in the cluster. So that's useful particularly if you have sort of elongated clusters where the majority of things are maybe quite far away. If we used single linkage, it would say those clusters are quite close together, even though they may be elongated and most of the members might be quite far away. Whereas complete linkage will give whatever is the farthest away points in those clusters. There's also centroid linkage. You work out the centroid of the cluster in the n-dimensional space and you get the distance between the centroids. There's average linkage where you take every pair of points in the cluster and you work out the average distance between all of them. But complete linkage is often the one that is used. So we'll do a simple clustering example just to show how hierarchical clustering works. There's some caveats here because what we're going to use is Euclidean distance so that we can see it graphically, and we're going to sample it between gene expressions. So we've got these large numbers for the gene expressions. This is really just to make the numbers sort of easier to see. The reality is that you would be using normally Pearson's correlation distance or the absolute value Pearson's correlation distance, and you would also be doing it between log2 expression values, since the log2 makes the values more Gaussian, so it's generally better for statistical analysis of all kinds. So these are caveats. This is what you normally would do for gene expression data, but we use Euclidean distance with just the gene expressions. So here's Euclidean distance, and the first thing you calculate is a similarity of distance matrix. So you take every sample, so we're going to cluster samples here, and you work out the distance with itself is 0, ALL1 to ALL2, well, you just take the 2 points and you work out a distance of 282. And you do that for all of the other pairs of samples. And this is what you use in hierarchical clustering. So hierarchical clustering then looks at the closest two samples. So this one is 282, ALL1, ALL2, and then it clusters them. And then it continues to look for the closest samples or the closest sample to cluster or clustered to cluster. I think it's good to see it graphically. So I've put all the points onto this sort of gene 1, gene 2. It's slightly stretched and slightly shrunk this, so the distance these don't look quite right, but we'll do hierarchical clustering here with complete linkage, and we'll show the dendrogram as it is built. So this is the similarity distance. So the first one we discovered was the ALL1 clusters to ALL2 at a distance of, I think it was 282. Yes, 282. So we join these two. These are the two closest points, and we form this. And then the next closest one, I think, is AML1 and AML2. Oh no, it's these two clearly. It's difficult with this stretched sort of axes, but yeah, these two. So that's AML1 and AML3 at a distance of 438, and then we get AML2 clustering in 632, and we then form a cluster like this. And then this one clusters in at 671, and we form a cluster like this. And then we're using complete linkage, so we choose the two farthest away points in the clusters, and then finally we form one cluster at a distance of 1561. And that's how hierarchical clustering process. So we build up clusters by choosing the closest points or clusters and then building it into a cluster and building up to a single cluster. So usually you then cut the diagram at some point, so here seems appropriate, and we get two clusters of the two subtypes of cancer. But lots of caveats. The example used only 2 genes so that we could visualize it. You may be working with all 20,000 genes, but you wouldn't be able to visualize it very easily. But hierarchical clustering would work. We used Euclidean distance, but we generally want to reflect patterns of gene expression profiles, so genes 1, 2, 4 are higher than average in both samples, or genes 3, 5, 7 are lower than average in both samples. So we use this Pearson correlation distance, or absolute value Pearson correlation distance. So the research article clusters different small round tumour samples, and we can cluster both genes and samples in this manner. So this is the GOLAB data, with all of the data being used, all of the genes, all 6,817. Usually that doesn't lead to a very good clustering because a lot of the genes may not be related to the sample type. But you can see that by and large it's clustered all of the AML samples here, and then by and large all of the ALL samples are clustered here, but there's a mixed cluster here with some AML and ALL, and there is one outlier, ALL here, which doesn't really cluster with anything. It may be contaminated with, say, muscle or fat, and that's why its gene expression profile is different from everything else. If we do this with the Khan et al. Data, then it clusters very well as well. So non-Hodgkin's lymphoma forms a very tight cluster, and rhabdomyosarcoma forms a cluster, neuroblastoma and Ewing sarcoma, and then these were out of sample data points, and you can see that these actually cluster in as well into the relevant clusters, and then some of these which do not cluster in so well, additional ones which are, I think that's osteosarcoma, so it doesn't cluster so much into the Ewing sarcoma cluster. So you can see clustering reveals subtypes of samples. It determines closely related samples, but you can also do it with genes. So I think it's worth introducing heat maps at this point. A heat map allows a very clear visualization of the expression values between many samples over many genes. What we generally do is a hierarchical clustering is carried out on both the samples and the genes, and this then gives the ordering of the samples and the genes, and then we put it out into a matrix in colour high expressed genes in samples with red, and low expressed ones with blue. Often red-green are used, but red-blue is better in terms of colour blindness. So here's a leukemia heat map. So these are the acute myeloid samples. So in this case we've selected a subset of genes which are significantly different at p equals 0.01. So we've got much cleaner clusters. So we've got a cluster of amyloid, acute myeloid leukemia, and we've got another very clean cluster of acute lymphoid leukemia, and then we've still got this mixed cluster of a few lymphoid and a few myeloid. But the visualization allows you to see why this might occur. The genes, when they cluster into largely two groups, the genes which are upregulated in the myeloid leukemia and downregulated in the lymphoid leukemia, and genes which are downregulated in myeloid and slightly upregulated in lymphoid. So this is what a heat map allows you to do. It allows you to see visually how the genes actually arrange themselves around the samples. You can see why these maybe don't cluster so well, because even though the red one, well, these ones are indeed slightly blue here, so they would fit in with the lymphoid leukemia, but they're actually also blue in these genes when they should really be red. So this is a bit mixed up, this one, and this is red, which is okay because it's myeloid, and then it goes to blue, which is okay, but it clearly isn't such a strong pattern of red and blue as these ones. So you get a slight mixing, and the heat map allows you to see that. If we look at the Can et al. Data heat map, then we have the different types of sarcoma all coming out in clusters with the samples, and then it's not shown the clustering of the genes, but this is certainly clustered because we've got a block of genes which are very high in the non-Hodgkin's lymphoma, and a big block which have low expression in the non-Hodgkin's. So there's certainly clustering of these genes. What you see here is that there's a block pattern. These first genes have high expression in the yellow sarcoma, but generally low expression in other ones. And then there's a block of genes which have high expression in the green sarcoma, and then the block in the red sarcoma, and then the block in the blue sarcoma. So it's a bit messier than the GOLAB data, but you can still see sort of this block structure. And that's what clustering allows you to do in heat maps, that you can visualize the different genes involved in the different samples. So that's clustering. So we've shown how clustering, well, one type of clustering, hierarchical clustering, works by having a distance metric and forming a similarity matrix, and then progressively clustering samples or genes which are closest together until you have just one large cluster, hence the name hierarchical clustering. This is used for detecting subtypes of disease, where we cluster samples and we get maybe 3 or 4 clusters indicating, of 3 or 4 very clear clusters indicating possibly 3 or 4 subtypes of that particular disease. Or we can also cluster genes, and the genes show groups of genes which are behaving in a similar manner across the samples, and that usually is indicating either the genes are co-regulated, they've all expressed on and off in the same scenarios, or they belong to the same biological process. So if they all act as enzymes in the same metabolic pathway, they may be all turned on and off in different samples at different times. And then from clustering the samples and the genes, we can develop heat maps which really show the relationship between the samples and the genes as a visualization. Okay, so in the next section we'll start talking about dimensionality reduction. I'll see you then.